This is actually a presentation that was prepared by Atem Ajri, who was a postdoc in our lab and also in collaboration with the IMB in Bordeaux, so between our lab, which is the engineering lab, and the mathematics department also at the University of Bordeaux. And this work that he prepared, unfortunately he cannot present it, so I will be reading his slides for you, is about maximum likelihood estimation on manifolds. So the main idea is the following. We all know that maximum likelihood estimators are under good enough conditions. They are consistent, they are asymptotically normal, they are asymptotically efficient. Yes, and the idea is when we are working, this is for maximum likelihood estimates of, let's say, real or vector valued parameters. When we are working on a manifold equipped with a connection, just any manifold with a connection, it's possible to mimic these results and obtain results, identical results for maximum likelihood estimates on manifolds. So it's fully general talk actually about maximum likelihood, parametric maximum likelihood estimation. So of course there are several kinds of Riemannian manifolds or other non-trivial manifolds that are interesting to our applications in signal and image processing. So manifolds of covariance matrices, whether they be real, Hermitian, Toeplitz, etc., are interesting to applications, image classification, EEG signals, radar signals, the such. This is one class of interesting manifolds, so it's interesting to estimate parameters in this kind of manifold. Stiefel and Grassmann manifolds, of course, also they are heavily used in computer vision. So this is second general class of manifolds that are quite important to signal and image processing. In addition to this Lie groups that are important in medical image processing and in robotics. Yep. So this is, I guess, if I'm not mistaken, covers most of the finite dimensional manifolds that you work with in signal and image processing. Then you could go to shape manifolds, which are infinite dimensional, but this is like a sum up of all the different kinds of manifolds. So the message here is, well, it would be interesting to estimate parameters that lie in these manifolds. Yeah? So of course, well, we all know maximum likelihood is, you know, this bold and brilliant idea that some people say turned out to be wrong. So this is there's a big debate for or against maximum likelihood. Still, maximum likelihood is considered a very good kind of estimation when we are looking for good asymptotic properties, because asymptotically it's supposed to be good. Well, in fact, even that is a debate among statisticians, but let's accept it anyway. So in any case, we can define maximum likelihood as soon as we have a parametric family of densities. Well, these densities can be with respect to any reference measure. Usually it's a Lebesgue measure. If you're in Rn, it's maybe a volume measure. If you're on some Riemannian manifolds, a Riemannian volume measure. But doesn't have to be. You can have any reference measure and then density with respect to this reference measure. And then you maximize the likelihood, and of course you take the logarithm. And the idea, if your data is independent, then you're looking at a function which is roughly like a martingale, of discrete time martingale. So this is the beginning to having good properties. So as I mentioned, why is MLE popular? Well, because in everyday life at least, it's consistent asymptotically normal, meaning in the usual sense, it's asymptotically efficient. So to first order locally, it's the best possible estimator in terms of its asymptotic covariance. Yeah. But that's a big debate also to statistics. But anyway, this is well-known property. And it's interesting to extend these properties to manifolds. So I'm sorry, so to give you an example which was mentioned repeatedly, so if we look at these so-called Riemannian Gaussian distributions, so these were designed in a certain way that maximum likelihood estimation of the parameter x bar is identical to computation of a Riemannian barycenter. So as we can see, we can also actually use this to gain insight into the problem of what is the best algorithm to compute a Riemannian barycenter. So to begin, we have results about consistency, and so under well-formulated results, we can show that maximum likelihood is always consistent. So, well, you have these results here, continuity with respect to the parameter, uniform boundedness of the expectation of the log likelihood, also, so to speak, uniform continuity of the log likelihood function, actually uniform continuity in L1. So Q of delta is the so-called modulus of continuity. Well, L1 modulus of continuity of the log likelihood function, and it's required to be uniformly continuous in this sense. So these are, well, strong conditions actually. Checking them would be difficult also, because in many cases, if you want to check condition 3, you're lost. It's impossible to check, yes? Unless you're working on a compact manifold and everything is bounded and you can use dominated convergence theorem and then you check this automatically. But in general, these are difficult conditions to check, right? Well, this shows actually also the infinite dimensional aspect of our problem, because fx of theta is a function. It lives in infinite dimensional. It lives in L1 of the sample space, and it's parameterized by theta. And the question, we have a curve in the space of L1 functions of our sample space. Is that curve continuous in the sense of the L1 distance? Yeah? So, moreover, actually uniformly continuous. But so because if the space theta, capital theta, isn't compact, we're looking at uniform continuity when we formulate this, yeah? Because the delta doesn't depend on theta. So difficult conditions to check, but in any case, in principle, it's possible to formulate general conditions such that maximum likelihood is consistent. Yeah? And this is why we like maximum likelihood. Even when these conditions are not verified, things still work quite often. And as you can see, it's possible to couch these conditions in a way that they don't refer to the presence of any Euclidean space, yeah, or underlying geometric structure. We only need that the parameter space is a metric space, or even just a topological space. So this is a very general result. So, as well, I'm repeating the same example. Actually, this shows consistency of the MLE. It implies consistency of the barycenter. It's remarkable that actually using results from stochastic optimization, there's a famous paper by Bhattacharya and Patranjanaru that shows the consistency of the empirical Fréchet mean, or empirical barycenter. So using techniques that are much less difficult conditions than these ones actually, because we have a specific problem involving Riemannian distance, so it's possible to relax some conditions. So Bhattacharya showed in his well-known paper consistency of the empirical Riemannian barycenter. And so actually in the case of the specific family of densities here, Bhattacharya's result covers consistency of the maximum likelihood, yes, under weaker results. So we have an interplay between results that we know already about Riemannian centers of mass, and then statistical results. So it's the interplay between geometric results and statistical results. So asymptotic normality, this is where we introduce a differential geometry, so to speak, actually. If you remember, proving asymptotic normality of maximum likelihood estimator means, well, first we assume that it's convergent, it's consistent, otherwise there's no meaning in saying it's asymptotically normal. Yeah? But assuming it's convergent, we can do a first order Taylor expansion of the likelihood function around the true value. Yes, and this expansion is going to have a zero first order term, because actually the score function, or the score vector, or score differential form is a martingale, so it has zero expectation. And so we only have a second order term, and we use the central limit theorem, and this gives us asymptotic normality. So key message here, it's possible to extend this proof immediately to any manifold with a connection. So all we have to do is, instead of doing the first order Taylor expansion of the likelihood function with respect to a parameter theta in Rn as we usually do it, we draw a geodesic from the true value, theta 0 so to speak, to the current maximum likelihood estimator, so let's say theta hat n. And we do a first order expansion, or in fact second order Taylor expansion along the geodesic. using the connection, and then we can prove asymptotic normality in that way. So the first order term in a Taylor expansion along a geodesic is given by the derivative, simply speaking. The second order, using the connection, the second order term is the Hessian operator of this connection. Yeah? And notice this doesn't depend on the connection actually. Everything I'm saying, you can choose any connection. So in any case, it's possible to, well, using what I just described, this slide describes the reasoning that or repeats the reasoning that I just described. Shows that we can carry out this kind of proof on any manifold with equipped with an affine connection, because we can do second order expansion, Taylor expansion along a geodesic, yeah, and use the central limit theorem and the fact that the expectation of the score is 0 because the score is a martingale. So we prove asymptotic normality. The question is, what is the asymptotic covariance matrix? Yes. So it's actually possible. So we know there's a quite well-known identity in statistics that says the Fisher information matrix is either the covariance of the score, or it's minus the expectation of the second derivative of the likelihood function. And this is due, so there's two ways of computing the Fisher information matrix, and this is due to so-called Fisher identity in statistics. So it's possible to show this is equally true in a manifold with a connection, because in fact we have an identity that says that the Hessian of the exponential of a function is equal to E times L, yeah, so L is the likelihood function, times the Hessian of L plus dl tensor dl, yep. So, because this is the second derivative, well now if we take expectation, this is 0, yeah, because the expectation of the integral of e to the power L, sorry, if we don't take expectation, if we take integral, this is 0 because the integral of the density e to the power L is always 0. So the Hessian of the integral is also going to be 0. It's the Hessian of a constant. So integrating here, this says the expectation of, minus the expectation of d2L is equal to expectation of dl cross dl. Yeah. So using this identity, which is true for any affine connection, we show the same result about the Fisher information matrix, and therefore we can prove that the asymptotic covariance matrix of a maximum likelihood estimate on a manifold is this matrix here, which we can take as a general definition of the Fisher information matrix on a manifold, because it's the covariance of the derivative of the likelihood. So to speak, it's right. So now we have shown that in fact on, well, any kind of, let's say, sample space, any kind of sample space that's a measure space, and any kind of parameter space that has just a well-behaved topological space, we have consistency of maximum likelihood under some conditions. And then if it's a manifold with connection, we can actually generalize asymptotic efficiency. Now, with regard to asymptotic, so this is the idea of the proof, as I was telling you. I'm sorry, I'm just reading the slides to you. I didn't make them. So we are now going to look at asymptotic optimality. Yeah. So why is this covariance matrix the least possible covariance matrix? So here we introduce some kind of new idea, in fact, of what is an estimating form, an estimating differential form. So we are going to say that if omega is a one form on theta, right? So meaning it's a random one form actually. So omega depends on x and theta. We say that it's an estimating form. If expectation with respect to theta of omega theta is equal to 0 for each theta. Yeah. So this is in particular true for the dl. dl is an estimating form, So this is in particular true for DL. DL is an estimating form. But let's say that in general, we want to look at any kind of estimating form. So in fact, each estimating form that we choose is going to produce for us a consistent and asymptotically normal estimate. Yep. So among all the estimating forms, what is the best one? What is the best one? So by carrying out the computations that we have already carried out, we can find the asymptotic covariance matrix. So, meaning if we choose as our estimating form the form DL, the score form, we obtain maximum likelihood estimation. But let's throw away the principle of maximum likelihood estimation and choose another estimating form, and we have another estimation method. Each estimation method is going to produce an asymptotic covariance matrix. So what is the smallest possible asymptotic covariance matrix? And the answer is going to be that it's the maximum likelihood covariance matrix is the smallest one possible. So the lowest asymptotic variance for estimating forms omega is omega equals the L, is the score form. Yeah. I want to mention actually that there's a very fine paper written by Smith a long time ago about Kramer-Rao lower bounds for estimation on manifolds. So here we have established asymptotic Kramer-Rao lower bound. Yeah, but in Smith's paper, he establishes a non-asymptotic Kramer-Rao lower bound. So it's for a fixed number of observations n, unknown fixed number of observations. And that's complicated. It involves the curvature tensor. Yeah. So what is happening here is we are converging, the estimator is converging to the true value. Therefore, we are in a very close neighborhood and things linearize. The effect of curvature does not appear. Yes? So imagine in our Taylor expansions that I told you about, we take the expansions farther, meaning instead of looking at the asymptotic normality of our estimator, we look at the asymptotic Edgeworth expansion of the density. So the terms in the Edgeworth expansion of higher order are going to involve the curvature of the manifold. And this is a very interesting thing to explore. I don't think anyone has looked at it. Is to actually find the connection between the role of curvature in higher order asymptotic efficiency through Edgeworth expansions. Yes, and this would connect because this is fully asymptotic result, and Smith has a non-asymptotic result. But using Edgeworth expansion, we can have something that is an intermediate asymptotic, yeah, between non-asymptotic and asymptotic, where the curvature appears in a simple way because Smith has a complicated expression in terms of the curvature. So actually the results that we have mentioned, they have applications to statistical tests because once we achieve asymptotic normality, we can have asymptotic chi-square. Yeah, but I think the time is up. So it's possible to devise asymptotic chi-square tests on manifolds using the results that we have shown here. So there's a practical application actually to this somewhat theoretical work. It has a truly practical outcome, which is the definition of asymptotic chi-square tests on manifolds. So thank you for your attention.
So do you have questions?
Thank you. Is it a correct statement to say that, or how do your conditions on the maximum likelihood estimation problem differ from just saying that, well, since I have consistency, with large probability I'm within a chart, and now I can write down the classical conditions if I just work in this chart, and say, well, according to the classical conditions, I have asymptotic normality of the maximum likelihood estimator, it will be asymptotically efficient, and so on and so forth. So, do your conditions differ from this? From the conditions you would get by this approach? Or?
No, they don't actually. So, remember the whole idea of the proof is the second order Taylor expansion. So, if you do it along a geodesic, we're doing it in a coordinate-free way, and we get a result that encompasses any coordinate calculation. Yes. if you choose a coordinate system, well, either you have a particular coordinate system, or in the end you have to look very intently at your expression, and although it's a coordinate expression, identify it as some as a coordinate expression of some tensor. Yes. So I guess to avoid that, we use a affine connection and a Taylor expansion method around the pieces. That's basically it, but of course we're right.
But if I would write it down in normal coordinates and basically see the same terms coming up.
Well, you can write it down in any coordinates. Yes.
Right.
So I'm sorry, please, I'm sorry, I just would like to say a further thing with respect to your question. So as I mentioned, because we're in an asymptotic regime, we are very local and we don't see the role of curvature. So your expansion in coordinates would become increasingly complicated as we add additional terms. And maybe it would be difficult to see the Edgeworth expansion and the intuitive curvature. But, yeah.
How often do the conditions which you mentioned for the consistency are not fulfilled? So is it some very exotic situation when the consistency don't hold, or it can be in some application?
Sure. I would like to invite you to read a paper. So there's a large debate actually. People shout at each other because is maximum likelihood a good method or not? There's shouting debate. But I would like to invite you, so there's a lot of literature, but I would like to invite you to read a paper by Lucien Lecam, so Lecam, called actually An Introduction to Maximum Likelihood, or something like that, along those lines. And it gives you a collection of examples where you see failure or success of maximum likelihood, and you can appreciate that by yourself. Yeah? So there's a whole debate about this. It's difficult to say. In many cases, maximum likelihood works asymptotically. Yeah? Some cases, even asymptotically, it's a failure. And Lecam did this extensive work about it with many, many examples. Yeah? If you look at the work of Lucien Lecam on this question. Of course, non-asymptotically, it's possible that maximum likelihood is a very bad estimator. So you have the famous James-Stein paradox and all these things that show you sometimes it's uniformly inadmissible. So it's a bad idea, so to speak, the James-Stein paradox in statistics. So it shows that in certain very simple cases, there exist estimators that uniformly dominate maximum likelihood, meaning there's no reason to use it whatsoever. And that's even for a Gaussian distribution, yes? But it's non-asymptotic. So there's this is a big debate among statisticians actually.
Many points.
So a case where it's inconsistent, I've never seen a case where it's inconsistent, but for the simple reason is that we always work with smooth densities, yes? Smooth densities that are nicely integrable, nicely equally integrable, equi-integrable, I mean, whenever you differentiate them and such. So I can't come up with an example like this, but as I said, I mean, this is interesting because there's a vast literature on this. Okay.
So we have two more questions.